Hello everyone, welcome to 𝐿ustraca. So in this lecture, we are going to discuss a very simple beam analysis problem. So what we are going to do, as you can see on the screen, that we have a very simple beam with some loading on it and some support conditions. We are going to analyze this beam manually. We will find the shear force and bending moment and also the shear force and bending moment diagram, and we will try to compare the manual values, the calculation results, and the diagram that we are going to create with the software results. Okay, we will create the same thing in the software, which is very vastly used software, StatPro. You can use any software, actually any structural analysis software. And what we will do, we will compare the results and we will see whether the calculation that we are doing manually, it is the similar results also we are getting in the software or not. Okay, so it's kind of software verification, or you can say also our result verification. Fine, so let's get started. So here you can see we have a very simple beam. If I just simplify this, so it is kind of like this. This is a beam with a, let me just change the thickness. So we have a simply support here. Okay, it is a pin support, sorry, pin support, and then we have a roller support here. Okay, and at 1 meter from this support, suppose if I name it as A and if I name it as B, and this point if I name it as C, so at C point we have 30 kilonewton point load applied. Fine. And if I see the distance, so from this support to the distance of the application of load, the point where the load is applied, it is 1 meter, and from here to the next support it is 2 meter. So the total, if you see, it is 3 meter length of this beam. Fine. So this is the information we have regarding the length of the beam, support condition, and the load. Fine. So now what we have, so I am considering that at least we know what these support conditions are. It is a pin support, so that means the translation along the horizontal direction is restricted. The moment is not restricted. Sorry, the moment will not come here, because here rotation is allowed. You can see here, if you see this image, it's like a what should I say, something like this. Suppose two plates and we have a rounded rod here. Now if I put something like this, so it can rotate like this, correct? So here, as it can rotate, so there will be no movement that we will be getting. These things we all know. I'm discussing if someone new, if any student, you can say those who are starting with their you can say structural analysis study, if they are seeing this video, so they may get some idea, or they have to see it later on after finishing their mechanics and you can say structural analysis subject. So those who are already know, so that is not an issue. It's a very simple problem. And now, what information also we have, generally when we see this kind of problems in the books, we do not have the sizes of the beam mentioned. We just have a beam and the load applied, and find this, you can say bending moment and shear force diagram and the results. But when you analyze the same in real life world, we have a beam which has a size, which has a thickness, or you can say which have a width or depth, and also some material is assigned. That means that beam will be made up of some material, maybe steel or RCC or something else, maybe wood, right? So that particular material, or you can say that due to the size of the section, that we also get some self weight. That means own weight of this particular beam, right? So that also should be considered in the structural analysis in the real life world, right? Only the 30 kilonewton load is not enough to analyze your beam, correct? So what we will do, first of all, we will, other than this 30 kilonewton point load, what is the load of this particular beam? Okay, so what we will do, we will find it in that way, that so I will write self weight of beam let me change the color. So it will be, if I do it in meter, so 0.3 meter means 300 mm multiplied by 0.5 meter. So we got the area multiplied by length. So you can find out for the whole length. So we will get in the kilonewton, or you can find out for a per length load. So what I will do, I will find for 1 meter. So suppose it is 1 meter, correct? So if I do it for 1 meter, what will happen? I will get the load per meter run, right? So 1 meter multiplied by density of reinforced concrete. So you all know it is 25 kilonewton per meter cube. So I will write it here as 25. As everything is meter, so I have written it as 25 kilonewton per meter cube in kilonewton per meter cube units. Okay, so the units should be consistent whatever you use. Now what will be the result for this? If I just calculate 0.3 multiplied by 0.5 multiplied by 25. Okay, so it is 3.75 kilonewton per meter. Okay, if I want to find out the total weight of this 3 meter length beam, so what I will do, okay, or if I find it in for 3 meter length, so it will be 0.3 multiplied by 0.5 multiplied by total length 3 multiplied by 25. Okay, or simply this value will be multiplied with 3. That's it. Here it will be replaced by 3. So 1 meter length is this. So obviously for 3 meter, this into 3. So this is the way we are finding. Now in that case, this meter will be removed because we are finding for the total length. Correct. So here it will be how much? Something around, if I just multiply a 3 with it, so 11.25. It will be 11.25 kilonewton. Okay, so this is the total weight of this whole beam. Correct. Now for analysis purpose, we will take this value. So what we will do to simplify this, we will add, we are making this problem as a problem given in the book. Okay, so we are saying that this is a beam, we have a point load and we have a uniformly distributed load. Okay, uniformly distributed load means the load which is at every section, it is uniform. The same value you will be getting. So it is 3.75 kilonewton per meter. That means this total load 11.25 is divided over the distributed over this 3 meter you can say length. So if you divide this 11.25 by 3, obviously you will be getting 3.75 by kilonewton per meter. Correct? It is uniformly distributed. There is nothing like here at this point B it is more, at C point it is less, then A point again more. No, not like that. There is no varying load. It is uniformly distributed. Okay. I'm going by this basics because those who are new, I'm saying those who are new to this subject, students starting with this subject, so that they can relate, even they are reading in the book, so that they can relate here. Okay, for the professionals it is obviously, it's like in the fingertip, so please pardon if you feel boring for this kind of explanations. So now we have found this problem, so this is our problem that we need to solve. Okay, so I will just what I will do now, I will use the formulas of static equilibrium, okay, or statics. So from the static equilibrium we have 6 formulas, but what are these 6 equations? So it is summation of fx equal to 0, summation of fy equal to 0, summation of fz equal to 0. That means all 3 directions. Okay, let me give some direction here. Suppose what we will consider that this y is positive y, this x is positive x. Let me write it properly here. Okay, let me finish it, then I will write. Okay, fz equal to 0 and summation of mx equal to 0, summation of my equal to 0, and summation of mz equal to 0. These are the basic equation of static equilibrium. Okay, that means summation of all the forces along x direction will be 0, summation of all the internal forces along y direction will be 0, summation of all the internal, that means the forces acting, external force, and the reactions that we are really getting. If we add this, the resultant will be 0. Okay, so this is what we have written. This is as per static equilibrium. Okay, so now for the algebraic equation, you can say formulation, what we will do, or algebraic operation I should say, it's a proper term. So we will consider one sign convention that this direction is plus y. Okay, this direction is plus x, and the clockwise moment, so moment clockwise, it is plus moment. Okay, maybe mz or something. I will just write it as suppose summation plus m or mu. I should write, not mu, summation of m, suppose plus m. So this is moment. Okay, so for the algebraic operation, I will use this sign convention for our solutions. Okay, you can change this sign also as per your requirement, but for throughout the calculation, that sign should be you can say consistent, whatever sign you use, right? It is the fundamentals of structural analysis, we all know. Not structural analysis, I should say fundamentals of mathematical operation. So now another thing, this is about the mathematical operations. I will write for mathematical, sorry, I should write for algebraic operations. Okay, so this is the sign convention for algebraic operation. We will consider the upward reaction as plus, the left to right you can say reaction or force as positive x, and this is my moment. Okay, or if I just not write, sorry, if I not write any axis here, okay, Control Z, I should write force actually. So rather writing y, it should be fy, and should be fx. Okay, and should be, and this one should be m, my moment. Correct? So one more thing that we need to understand is the direction of the moments. Correct? Direction of the moment. So suppose we have a beam like this, and if it is bending like this, this is for algebraic equation. Now we are talking about the bending moments. So if it is bending like this, so here we are saying that the bottom, it is in sagging, or you can say this condition, we can say it is sagging due to application of load. So the moment we are getting here, it is something like this, something like this. Correct? It is sagging, it is bending like this. So this we will consider as sagging, we will consider as positive. Okay, you just keep this algebraic equation apart. Now this is about the moments. So we will consider the sagging as positive when the beam top is in tension. Now here this bottom is in tension, top is in compression. Correct? But now if the bending is something happening like this, okay, so this top is in tension, now bottom is in compression. So this condition, what we call it? We call it as hogging. Okay, and this hogging we will consider it as negative. Okay, so the moment will be something like this. You do not compare with the above one. Okay, this is different, this one is different. So this is hogging, that is sagging. Correct? In case of shear, again, in case of shear, if you see here, let me draw it properly. So if I draw shear in beam, so if the shear is clockwise mean if you see the direction of force is something like this. Okay, so clockwise shear, so I would write it as clockwise shear, we will consider it as positive. Okay, and anti-clockwise shear, so it is something like this if you see. Okay, so I will write anti-clockwise shear as negative. See, I am writing all this considering that you know the fundamentals, basics, and we are just brushing it up. Okay, please, those who are very new, then it may not be you may not be understanding all this directly itself. Okay, here itself, so you need to study the fundamentals first, and then if you see, it will be I can say you can relate properly. Correct? So clockwise shear we considered positive, and anti-clockwise shear we are considering it as negative. So this is for the bending moment and shear force diagram, and we'll be drawing, we'll be considering this sign convention, and for algebraic solution or operations we'll be I can say considering this sign convention. I hope it is clear to all of you. Okay, so now let's come to our problem. Let us draw the problem again. Here we have a beam, it is pin supported here. Okay, we all know this is the symbol of pin support, and this is a roller support. Okay, roller support means it can move along this direction like a roller, it can move along this direction. Okay, but the other direction is restrained. I should say, as it is a 2D plane, so obviously it will move only along this and this axis, x and y. Okay, correct. So other direction we should not consider, and as it can roll around, it can rotate, so there will be no movement also. Correct, because it is kind of simply supported, and we have a 30 kilonewton load here as point load, and for the self weight we consider that there is a uniformly distributed load of 3.75 kilonewton per meter. I named it this particular as A, C and B. This distance is 1 meter and this distance is 2 meter. Correct? So this is our problem. Fine. So let us now solve it. Now to solve this, first of all, what we will do, we will use the you can say equations of static equilibrium. So if I consider, first of all, what I will do, I have to draw the free body diagram of this particular thing. So if I draw the free body diagram, if you see, so I will write as free body diagram. So what we do in free body diagram, we just replace the supports with the support reactions. Correct? So this is my beam, as this is the pin support, so I will have a vertical reaction because it is restrained. Beam cannot move along this direction, so I will get a restraint. It is y direction, so it is Fy, or I should write it as it is a point A, so it will be Ay. This cannot move along this direction also, along the horizontal direction also, so here also I will get a reaction. Okay, so it will be Ax. Correct, but it can rotate. It can rotate like this, so there will be no moment, so I will not write the moment here. Fine. The other direction, if you see, it is the roller support, so only the vertical direction it will not be moving, so we will get reaction along this direction. Suppose I will name it as By. It can move this direction along the horizontal direction, so there will be no horizontal restraint, no horizontal reaction also. And one more thing is, as it is a simply supported, so there will be no movement also. Like it can rotate also, right? As it is just supported on the roller, so it can rotate also, so there will be no bending moment. Correct? Then we need to draw the forces. We have 30 kilonewton load at 1 meter distance, and we have a uniformly distributed load due to the self weight, which is 3.75 kilonewton per meter. So this is the free body diagram. Should also draw this lengths. Fine. Now what I should do, let us apply the you can say equations of equilibrium, static equilibrium. So summation of fx, suppose we are taking this x direction, so summation of fx equal to 0 if we are considering, then that implies, if you see along x direction how many reactions we have or how many forces we have, so you can see along x direction only this ax we have. Okay, no other force or reaction. So what we will do, we will write it as, that means ax equal to 0. So we already got the value of ax. So there will be no, that means there will be no horizontal reaction, as there is no horizontal force, right? There, if there is a horizontal force, then only you will be getting horizontal reaction. Okay, so there will be no horizontal force and no horizontal reaction. So this is solved. Now it is, you can also remove this particular sign also from here. Let it be. Next, if I apply, suppose moment about, if I apply moment about a axis, so I know this clockwise moment is positive, correct? Clockwise moment is positive. So if I take moment from this point A and I have B and C, now you see at this point which are the loads that will be creating moment. If you see, first one is this 30 kilonewton load that will create moment. How? This is my beam, suppose I have a 30 kilonewton load here, okay, and I have this point A. What will be the direction of moment? Obviously it is rotating about this point, so the direction of moment will be this direction. It is clockwise, so it will be positive, correct? One more, if you see this B, as I am talking about this point, so these forces will not act, these forces will not create moment, as these forces are acting at the point itself. To create a moment, we need a distance, we need a lever arm, right? So now if I go here at this point, B point, we have a reaction By. So this reaction By, this is first one. The second one is, if you see, I have a whole length, this is my point A and I have a By. Okay, so this By force acting upwards, so here it will create a moment like this. So as it is anti-clockwise, so it will be minus negative. So I am taking sign convention of this one for algebraic equation or algebraic operations, right? So you can see clockwise moment is positive, anti-clockwise moment is negative, correct? So it is a negative one. One more load I have, which is the self weight of the beam. Now this self weight of the beam 3.75, if I want to find out the equivalent point load, the equivalent point load will be 3.75 multiplied by 3. So ultimately we are getting this 11.25, and this 11.25 will be acting at the center of the beam, as it is uniformly distributed load, center of the beam. Okay, so it will be 11.25. Sorry, I should write it something like this. So equivalent, sorry, Control Z. So equivalent load of this UDL, it will be 3.75 multiplied by 3 equal to 11.25 kilonewton, and it will be acting at the center of this beam. That means 1.5 meter. So the next one, if you see, it will be same as the first one. So it will be this 11.25 kilonewton, and about this A, so it will be positive moment here. Correct? So these three moments will become. So if I just write summation of moment at A, moment about A is 0, I am considering the equilibrium. That means 30 into this 30 is acting at 1 meter distance, correct? This is 1 meter distance, so it will create the moment. So the moment sign will be plus, so I will just write 30 into 1, it is the plus value, plus next positive is 11.25 into 1.5 meter, so it will be 11.25 multiplied by 1.5 Now the next moment is negative. Okay, so it will be minus, I should write it, minus by into 3, right? So 3by. I have just directly written 3 into by because this total length is 3 acting at the end, so it will push and it will create this kind of moment at the A. So minus 3by. Fine. So if I just want to find out, so it will be 30 plus 11.25 into 1.5. So it will be, let us 11.5 1.5, so 16.875 16.875, okay, minus 3by equal to 0. I should write it here equal to 0 because I am writing summation of ma equal to 0, correct? Now if I find out the by from here, so by will be 15.625 kilonewton. Okay, so I have this by, right? I have this by, correct? Okay, so now I have the by. So this is the, basically this is the, what is this shear? Actually shear is the whatever force you are applying, that force will be distributed to the two ends and we will get the shear at the ends. Okay, so direction of force and direction of shear will be always equal, correct? So here if you see, we are getting by. We will see this, we will again prove it when we will be finding out the shear force. So this is by support reaction at by, which is 15.625 kilonewton, correct? Now if I use another equilibrium condition, which is summation of Fy equal to 0. So if I see what are the forces we have, so first we have these two reactions, Ay plus By. I will just write Ay, because this is upward, so all the plus values, By. Now if you see, loads we have 30 kilonewton and this 11.25 kilonewton, and they are downward, so negative, so minus 30 minus 11.25 equal to 0. By we know 15.625, so if you just replace this, we will get from here Ay equal to 25.625 kilonewton. So we got the Ay from here. I hope it is clear. Okay, how we have done, I have just replaced this Py, which is 15.625. so if you see here, my 30 will be going there, so 30 plus 11.25 minus this By, which is 15.625, so I am getting 25.625. okay, this is how I got the Ay value. Fine. Okay, now what I will do, now I will take, let me draw the problem here. This is the problem. I have a Ay, I'm drawing the free body diagram only. Ax, which is 0, By, I have a load acting here, which is 30 kilonewton. I have a uniformly distributed load acting 3.75 kilonewton, for which the equivalent load is here I'm getting, correct? So now this equivalent load is not required, let it be. Okay, and then this is acting at 1 meter and this is acting at 2 meters. Fine. Okay, now first what I will do, this is my point A, this is point C, and this is point B. First what I will do, I will take a section here, suppose somewhere here, okay, somewhere here, and what I will say that this is my, this is suppose at x distance from the support. So at x distance from the support, here case 1 is, suppose I will write case 1, if you see this x, it should be greater than 0. If I consider this is my 0 point and this is my 3 meter point, correct, length. So this is my 3 meter and this is 0. So at x should be greater than or equal to 0 and should be less than or equal to 1 meter. This is my first condition, case 1, because I have taken x here and this distance is 1 meter. So x should be less than or equal, greater than or equal to 0 or less than or equal to 1 meter. So in this condition, if I take the free body diagram of this particular part, so how it will be? So it will be, this is my beam, I have AY. I will not draw the AX because AX equal to 0. So if you want to draw, you can draw it and you may write directly AX equal to 0, correct? Okay. And so no need of writing it actually, as it is 0, let it be. Let not take some more space. So AY, and now as I have given a section here which is at x distance from the support, so we will get some internal forces. So first we will get, as the direction of force is along downwards, so shear will be downwards. So this is my shear, I should write Vx, and the moment, if you see, I have this uniformly distributed load here, 3.75 kilonewton per meter. Okay, so as I have the load, so now that load will be acting where? 3.75 into x, this is the load, and it will be acting at x by 2. So it will be acting somewhere here, which is x by 2, and this load, which is equivalent point load to this in UDL, so it will be 3.75 multiplied by 3.75 into this L length, so x kilonewton. This is my equivalent point load, right? So for this, I am taking, suppose, moment of this particular point. So this point is C actually. This point is C. So this moment direction will be obviously along this direction. Load is acting this direction. So if this is my point, loading acting here, so obviously it will rotate the point like this, correct? So this is my moment, which is, suppose, m Vx, and I should write, mx Vx, should I write, or let it name it as Vc and mc. Okay, here at C point and moment at C point. No, this is not C actually. What should I write? This is x. Okay, let it write it as bx and mx only. Okay, just for our understanding, some name we have given. Fine. So now if I apply the you can see equations of equilibrium, suppose summation of Fy equal to 0, so that implies, you can say, Ay plus, so Ay, now Vx is downwards, so minus Vx, this load is also downwards, correct? This load is also downwards. What is this load? Total load. So this load is minus 3, or I should write it properly, 3.75 x, as it is not moment, just the load, so there is no need of this length, half of this, something like this, because when we are finding moment about this point A, then we need this length. Now we need the total force acting, so it is 3.75 into x. Okay, downwards, so all minus. Fine. So we know the value of Ay also. We know the value of Ay also. if I just name it, suppose this is equation 1, this is equation 2, so I may write it as, from 2 we know ay equal to what, how much it is, you can see 25.625. so 25.625 minus vx, this equal to 0, okay, minus 3.75 x equal to 0. Fine. So vx equal to, I should write 25.625 minus 3.75 x, correct? So this is my one equation. Okay, this is in kilonewton. So I will name it as equation 3. Okay, we will check, we will you will once we progress with the calculation, then you will understand why we are finding it. Actually, though it is not required directly, we can write from the values we have got, but just to proof check, or just to show you that yes, exactly we are getting it the same. So that's why we are doing on this. Now if I take moment about this x, okay, moment about this x length, suppose, or I'm writing, naming this point as x, okay. So moment about x, if I write mx equal to 0, then how much it will be? See, this mx, it is anti-clockwise, so it will be negative. So I should write implies minus mx. Then how much other than this, what it will be there? So as I am rotating about this point x, suppose, so now this ay will come into existence. As this ay is acting upward, so it will create a clockwise movement to this point. So like this is my point, ay is acting here, so it will be a clockwise movement, correct? So I will write it clockwise movement, so plus ay into x. Okay, so I got the moment. Then we have this load at x by, at how much distance? Yeah, x by 2 distance. Obviously this is also x by 2, correct? This is also x by 2. So I will write, now this will create again anti-clockwise movement, okay, at this point. So it will be, what is the load? Minus load is 3.75 into x, and that load will be acting at x by 2 distance. So this is my total moment, correct? This equal to 0, is equal to 0. So how much we are getting? We are getting minus mx plus ayx minus 1.875 x square equal to 0. Now if I just find out, I can say ay I can replace with 25.625. okay, so I can write mx equal to 25, I'm taking everything at that side, 25.625 x plus 1.875 x square. See this negative, see when this side is, it is going this side, it will be negative, and this will be also, this will be let me see, this is negative. Did I do anything wrong? Let me see. 3.75 3.75 into yeah, it is correct only. 3.75 into x to x by 2 negative Let me just see what I am doing. Summation of mx, right? So it is anticlockwise moment. In this case, it will be negative only. Correct? This moment will be negative only. I think actually I have done this calculation earlier and I think I have done mistake here previously. Now it is correct. So this sign convention, it will be negative. Okay, 25.625x minus 1.875x. I'm not sure whether I'm doing it correct or not. Let me just do it. Okay, let me just do it properly. Minus mx. Okay, this is plus, it will become minus. This is minus, it will become plus. Now if I just multiply it with plus, it will minus. Okay, so I did correct only here, I feel. Ay into ay multiplied by x, it is this x. So plus mx is negative. This is acting at, okay, fine. So I have done it correct only. I'll just remove this. So it will be negative. We will see what it is actually. Fine. We got this one, which is my equation 4. I'm not sure whether I have done any mistake anywhere. Just feeling like I have done any mistake somewhere. Okay, if it is 1, okay, fine, let it be. Then what we will do, now we got one condition. Okay, we found one condition. Now next we will similarly we will create another section, and we will take the section now in between these 2 points C and B.